Electronic configurations are an attempt to specify the location and energy of electrons. The electronic configuration of hydrogen, for example, is 1s1. This first number 1 pertains to the shell number. The s is the subshell, and the superscript is the number of electrons in that subshell. And what we're going to do is to look at the electronic configurations of a number of elements, and as we do so, we're going to follow the rule that we'll fill spaces closest to the nucleus and then move farther out. It's a little bit like a lecture room where students come in, they sit as close to the front as possible, and then later students fill those spaces behind them. For hydrogen, to say that its electronic configuration is 1s1, well, if we envision this as the atom again, and here's the nucleus at the center, the s subshell is sort of spherical shaped. It's like a basketball. And what this 1s1 says to us is that the electron of hydrogen is in this basketball-shaped space, fairly close to the nucleus, and that's about it. That's all we can do. And again, it's because the speed the electrons have and their very small sizes that prohibits us from being more specific. The electronic configuration of helium, the next element, element number 2, it has a total of 2 electrons. Well, the s subshell has 1 orbital, and remember that an orbital can hold 2 electrons, so the configuration is 1s2. Let's go to lithium. Lithium is element number 3. We've filled the first hotel. It's an unusual hotel. It has just 1 floor, the S floor, only 1 room in that S subshell, and it can hold 2 electrons. Once it's filled, the next electron for lithium has to come out a little ways to the second hotel. The lowest floor, the lowest subshell in the second hotel is the S, so it's 2s1. Total of the superscripts is 3, that's the element number. Beryllium, well, it would be just like this, except we're adding 1 more electron. So beryllium will be 1s2, 2s2. Boron, element number 5, fills the first hotel, the S floor in the second hotel, and so the next electron, beryllium's 5th electron, has to go to the P subshell, P1. Carbon, well, you know what it's going to be now. Carbon's going to be 2p2. Nitrogen, everything that we had before, it's only the last electron that's going to be different, 2p3. Oxygen, 2p4. Fluorine, 2p5. Neon, 2p6. Everything else would be the same. Because of this, sometimes we introduce the term distinguishing electron configuration. And that is the electron configuration of the outermost electron, or the very last one. And that's a little easier to write down. And both are important, though, the complete electronic configuration and the distinguishing electron configuration. Well, we've filled the first hotel, and now the second hotel is full. So when we come to sodium, element number 11, we'll have to go to the third hotel. Lowest floor in the third hotel, the S, it's going to be 3s1. Magnesium, element number 12, so the total of the superscripts would be 12 in this case, is going to be 3s2. That fills the first floor in the third hotel. The fourth hotel, I'm sorry, the next floor, the 3p, is where aluminum's outermost electron will have to reside, 3p1. Now you can predict the elements following that are going to be filling the 3p2, the 3p3, and so forth. Finally, we'd have argon at 3p6. What we've been doing is filling electrons one at a time in the spaces about the nucleus. We could call that the order of filling of shells and subshells. And you could memorize this line or have it on your sheet of notes: 1s2, 2s2, 2p6, 3s2, and so on. That would guide you if you were to be asked what the complete electronic configuration was of any element. Or within the text, there's sort of a vertical diagram that shows you the order of filling shells and subshells. But my favorite is to use the periodic table of the elements. It's like a road map, and you'll see that it's very, very easy to come up with the order of filling using the periodic table. Let's do that. Here we have the periodic table of the elements. These tables come in different colors depending upon what the authors are trying to emphasize. Element number 1, hydrogen. Remember, its electronic configuration was 1s1. The distinguishing electron configuration of lithium, 2s1. The distinguishing electron configuration of sodium, 3s1. And from that pattern you might gather that, hey, all of the elements in this first column are going to end in s1. And all of the elements in group 2 are going to end in s2, and so forth. Elements in the same vertical column, and the vertical columns are called groups, have similar electron configurations. Here's the periodic table drawn to emphasize electron configurations. Elements within this first group end in s1. Elements in the second group, s2. Let's skip this center section for just a second. We've looked at lots of elements that have P1, P2, P3, and so on. And those are the 6 columns over on the right-hand side. In the center section, these are elements filling the D subshell. And at the bottom, the 2 rows, elements that are filling the F subshell. And knowing this fact gives you tremendous ability now to see how the Schrodinger wave equations apply. In the S area, there are 2 columns, just 2, reflecting the fact that the S subshell has just 1 orbital. And so we can hold at most 2 electrons in those areas. The P subshell has 3 orbitals, so we can pack 6 electrons. We have 6 columns. The D, well, it may be tough for you to remember that there are 5 d orbitals that can hold a total of 10 electrons in those subshells. But if you came to the periodic table and counted these spaces, you'd see that there are 10 columns. Down here in the F area, there are 14 columns, meaning that we can put 14 electrons in. 7 F orbitals could do that. So there's a nice vertical grid system pertaining to the periodic table that gives us information about the electron configurations. There's also a horizontal grid system. The horizontal rows, you know, are called periods. And for the shell numbers for S and P electrons, for S and P elements are the same. The period number and the shell number are the same. Hydrogen and helium are in this first horizontal row, the first period, and remember that they're 1s1 and 1s2. So the first period is filling the first shell. In the second period, we have lithium, beryllium, and then these elements to the right, they're filling the second shell. In the third period, we're filling the S area of the third hotel and the P area of the third hotel. We can sort of track our way through the periodic table and come up with these electron configurations. Beginning in period 4, we have 4s1, 4s2. Let's skip the center for just a second. Come over here to the P area. This would be 4p1, 4p2, 4p3, p4, p5, and 4p6. Now, coming back to the center, these are the Ds. And we see one of the exceptions. There are a number of exceptions to this order of filling, but they're predictable. And the two biggest exceptions come with the D elements and the F elements. It turns out that the third floor, the SPD, the 3D subshell, doesn't fill right after the S and the P. It waits until the 4s2, and then we have the 3D. That would be a little tough to predict, but based upon chemical properties of elements, we believe that that's the case. So in other words, to summarize, here in period 4, have 4s1 and 4s2, and then these are the 3D elements. The Ds drop back 1. In the fifth shell, these would be the 5s1 and 2, the 5p6, but the Ds would be the 4D, the 5D, and the 6D. Let's see if we can rationalize this exception. Here's one of the exceptions in the periodic table. The 4s fills before the 3D. Let's see if our hotel analogy helps us. Here's the convention center. Out here's the fourth hotel. We've got to walk out there. And if we had a room in the third hotel on the D floor, when we get out as far as the third hotel and look at all those stairs we've got to climb, it could be that the spaces here in the fourth hotel on the first floor look a little more attractive to us. And that's what happens. The 4s fills, then the 3D. And that pattern of exceptions goes through the periodic table. Let's go up and look at our periodic table again and see if we can practice a little bit. Knowing these trends and using our horizontal and vertical grid system, let's see if we can come up with distinguishing electron configuration for just about any element on the periodic table. Let's pick some elements and see if we can come up with the distinguishing electron configuration. If I ask you what it was for magnesium, for example, you'd look at the periodic table and say, well, hey, it's in the S2 column. It's in the third period. So its distinguishing electron configuration is going to be 3s2. Jumping across, well, let's pick arsenic. Arsenic is on the right-hand side. I know it's in the P area. And it's going to be P1, P2. It'll be in the P3 column. And arsenic is in the fourth period. So its distinguishing electron configuration is 4p3. Let's pick something way down here. Here's element 82, lead. It's in the P area. P1, P2. It's going to be a P2 element. Let's see what shell is being filled. It's period 6, 6p2 would be the distinguishing configuration for lead. Let's look at something in the D area. Here's iron, number 26. I know that it's going to end in D. It's filling the D subshell. 1, 2, 3, 4, 5, 6. It's the sixth column over in the D subshell, so it's going to be D6. It's in period 4, but remember the D's drop back 1, so it's 3D6. Or if we had zirconium, element number 40, second D column, D2. It's in the fifth period, but the D's drop back 1, so it'll be 4D2. So just to summarize, if it's an element in the S or the P area, the shell and period number are the same, but if it's in the D area, the D's drop back 1. As elements were discovered, many of them in the 1800s, a Russian chemist by the name of Mendeleev tried to make some sense of what was being discovered and noted that many of the elements had similar properties. And so he came up with an arrangement where elements with similar properties were placed in the same vertical columns. For example, lithium, sodium, and potassium all react pretty vigorously with water. Or fluorine, chlorine, bromine, and iodine have properties that are very similar. So elements in the same vertical columns have similar chemical properties. That's probably the most important fact from the entire semester, because if you know that, then you know many of the chemical properties up here. You know that all life is based upon carbon, and if we were to find some other form of life that had a different basis, well, maybe it would be the element silicon. Or if we were after gold and found a copper deposit, maybe we'd also have some silver and some gold in that same deposit. What we've learned with electronic configurations is that we have also placed elements with similar electronic configurations in the same vertical column. Mendeleev didn't realize that he was doing that, but we see now elements in the same vertical columns have similar chemical properties and similar electronic configurations. So it's pretty obvious that electrons, the properties of electrons, help determine the properties of elements.